At this, and we're trying to figure out what's fishy about it. Something about it looks a little suspicious compared to the ridge regression we were doing last time, and that means that we're not going to get a good result. Let's see if you guys had some ideas of what was the thing that was looking weird. Okay, someone said multicollinearity. Great $100 word with many syllables and hard to understand. We're going to talk about multicollinearity later. Some people put multicollinearity in Project 1, so I want to talk about it because I think you guys could use a lesson in what it means. Okay, scale is on the right track. Good. Maybe this person ran out of characters. Good variance also has coefficients decrease. 4 people, I don't know. Great answer. If you don't know, yeah. Is there something wrong? Yes. No. All the coefficients has equal. This is starting at a very specific idea. If you look at this picture, okay, there's these 3 on the outside, the red one, the blue one, and the green one. But the rest of them, all the other coefficients are over here hanging out at 0 and don't change. All the coefficients are just like flat function. They're barely changing. That is a great observation. Highly correlated data. Again, this is the same kind of idea as multicollinearity, and I guess you guys are like warned about this like a boogeyman, like it's going to come get you. The highly correlated data will come eat you at night when you're sleeping. I don't think this has anything to do with highly correlated data. So it's good. It's a good guess, and we'll talk about when you have highly correlated data, it does something, but it doesn't do the things we're seeing. Okay. So shrinkage factor is the amount we're using. Not using the whole training set. That if we didn't use the whole training set, then we wouldn't have. We need to have some test set to work on. So it's true. Like we could improve the model a bit by using the entire set, but then we wouldn't be able to say how well it's doing. So in the realm of doing things that we can understand, we have to do it this way. Okay. Of all these, it seems like we don't really have an idea. What's the closest? The fact that they're always equal, and scale is also related to this. What about scale do you see in this picture related to the same thing I talked about? There's something kind of unsettling about the scale here. Does anyone want to take a stab at saying what's wrong with the scale? Yes, okay, this is great. So the features are in different scales. So the features, I think, would be these things, which are the at-bats, the hits, the home runs, and so on. These are at different scales. Let's look at some of the data. So in this, we have the coefficients, and if we look at the actual features, those are numbers like this, these numbers. So look, put-outs are 632, or 800. Put-outs, I guess, is something, when you're playing every round, you can have a put-out. Whereas something like some of these other numbers, like division, is either 1 or 0. So the features are on very different scales here. This feature, this column that I'm highlighting, is either 1 or 0. This one over here is like hundreds or thousands. Here's another one that's 1 or 0. So the features are on very different scales. All right. That is a true statement about the universe. On the housing data set, I said you don't need to worry about that. It's okay if the features are on different scales. But if you look at what's going on here, because the features are on different scales, it causes something else to be on different scales. What does it cause to be on different scales? Looking at this picture. The features, the numbers in these columns are on different scales, and that causes something else to be on different scales. And you can see it in this diagram. You can see it over here. If you look like so on the left-hand side here, here's the regularization parameter is tiny. That is almost no regularization. No, like it's almost like ordinary least squares on the left-hand side. So what do you see about those values?
The negative coefficients are overpowering positive ones, I think.
Yeah, so they are very, very negative compared to these ones. This is negative like 125, and this is like 0.1. So the features were on different scales, and that causes the coefficients, these are the coefficients, they are also on different scales. So, and in fact, we can look at them directly. So you can look at the picture and just visually see some of them are much bigger. There's this one is very, very negative. That one up there is very, very positive. You can also read the list of coefficients, and you can see that some of them are much bigger than others. So look, here's one that's negative 116, and this is like 0.2. So one of them is 200 times bigger than the other one. And that really comes directly from the fact that the features are in different scales. So that the features are in different scales. How are the features and the coefficients related? Well, we're using the formula. Here it is from last time. The formula is you multiply the coefficient, you do the coefficient times the feature, right? So if the features are very large, then the coefficients have to be very small so that when you multiply them together, you get some reasonable addition to your y, right? And it has to sort of match. So different features and coefficients, they can be on different scales, but coefficient times feature always has to be on the right sort of scale of having a meaningful impact on the thing you're trying to predict, the salary, right? So coefficient times feature should always be on the order of like hundreds, right? It should always be like hundreds, and the reason is the salary is always like some number of hundreds. So if you have something like putouts that's already in hundreds, then you multiply it by a coefficient. The coefficient can be like 1 or like 0.1, that makes sense. If you have something that's like 0 or 1, like new league, then the coefficient will be like hundreds, right, to multiply it, to make it work. And that's exactly what we see. So some of the coefficients, like division and league, those are things that are 0, 1 valued, and those have in the size of hundreds. And then things that are big numbers, where's putouts? Let's find putouts. I would love to know what a putout is. Someone who knows baseball should tell me. Okay, putouts is 0.28, right? So you multiply the big number by 0.28. Okay, so these things are all on different scales, which is perfectly fine. Like in your housing data set, I said, don't worry about that. It's fine. Okay, who cares? The betas, some of them are big, some of them are small. It's all okay because when you multiply them together, they cancel out, right? If the coefficient is really big and the feature is really small, great. Multiply them together, you get something normal size. If the coefficient is really small and the feature is really big, that's fine too. You multiply together, it's fine. And the betas are found automatically to be the right size. Like if you multiplied the x's all by 10, then all the betas would shrink by 10, and you have the exact same thing at the end of the day, right? Because you would say like beta times x, and then some naughty person comes in and says, let's multiply by 10, ha ha ha. And you say, okay, that's no problem, I'll just divide by 10. And then they cancel out. So it doesn't matter what's going on if you're just doing linear regression. Okay. But something is wrong here, because we're not just doing linear regression. What are we doing? We're doing ridge regression. So why does that matter? Why does that change things? Okay, so let's make this statement. For linear regression, it is fine. For ridge regression, it is not fine. There's a problem. And I want you guys to think about the problem. So I'll give you another 2 minutes to think, talk to your neighbors. What is the problem? Before it was perfectly fine for linear regression. Now for ridge regression, it's an issue. Try to remember, what is ridge regression? What are we doing? Take 2 minutes, talk to your neighbor, see if you can think of what it is, and then I'll tell you. Okay. So, okay, it's been 2 minutes. Let's have a little discussion here. Does anyone have any ideas? What is the problem? Before it was perfectly fine. Some of the betas were big, some of them were small. Who cares? It's all fine. You multiply them by the x's. But now we're doing ridge regression, and there's a problem. Did someone spot what is the problem? Yeah.
Yeah, so we are finding some kind of in last lecture we saw that 0.9 number, the lambda or something.
Mm-hmm.
So we are trying to optimize the function. That's our goal. Now
Yes. Wait, hold on. Let me stop you. We're trying to optimize our function. What is the function? I think this is important. Okay. Does this work? This doesn't work because the mouse is moving. Let's turn the mouse off. Okay. Optimize the function. Okay. What is the function?
So we are multiplying some lambda with all the coefficients.
Well, okay. In ridge regression, all the coefficients can be different numbers, and we're trying to. And we are trying to optimize something. Do you remember what the formula is for what we're trying to optimize?
It's the penalty term, lambda times integration of a function that captures the wiggles.
Yeah. Well, okay. So let's look. So I think the right way to think about it is it's what we were doing before plus a penalty term.
Yeah.
That's right. Okay.
Yeah.
What were we doing before was mean squared error. Mean squared error. The MSE. This is the same as ordinary linear regression. This is the ordinary, right? The ordinary mean squared error, but then we did plus a penalty term, and then we did plus the penalty term. And the penalty term had a coefficient. This is where we put a coefficient. So sometimes people call it lambda. Last class we were using lambda for the shrinkage factor. So lambda is the James-Stein estimator. It's how much you shrink things. So you take whatever the coefficient was, you multiply it by lambda. That is different than the size of the penalty term, which we call alpha. But they both have the same effect, which is they shrink things.
Yeah.
Well, actually they have kind of reverse effects. Because if lambda is like 0.0001, super tiny number, then you shrink a lot, right? But if alpha is 0.001, that means you have a very small penalty term. So they're actually like inverses of each other, but they do the same thing. They control how much you're shrinking. So let's stick with an alpha, and this is the size or the weight, the regularization parameter, and if it's big, that means big penalty term. Okay, parameter, and that is what is on the x-axis in the graph, right? Oh, when you turn the mouse off, it turns out it doesn't work anymore. Okay, let's click back on here. So that's what's on the x-axis here, is the size of that alpha parameter. So here it's 10 to the minus 2, 0.01, and over here it's 1,000, okay? And so when it's 1,000, that's a big penalty term, and everything, all the coefficients are pushed to 0. Okay, so this is when you say optimize the function, this is what we're optimizing. Some people call this, I guess, the ridge objective function or something. You know, you can give it a fancy name, but it's the mean squared error plus alpha times the penalty. I stopped you at function so we can make sure to get it right. Keep going.
Yeah. So now this parameter alpha, it is dependent on these coefficients, and I think that the high difference or in their scales is causing the alpha to be
Okay, great. This is
we are not able to predict a great alpha for.
Gotcha. Okay, so this alpha, it is true in the James-Stein estimator. That lambda JS, that one depended on everything. But then we said, okay, what if we just fix a lambda? And then we said, what if we just fix an alpha? So this alpha doesn't depend on anything. We are the rulers of alpha. We just come with an alpha and we say alpha is equal to 1. And then we see what happens. We optimize the function, and so we get to choose alpha. This is the loss, and it depends on the parameter alpha and all the data and all that, right? So we get to choose alpha, which is why it's on the x-axis. We can pick any alpha we want, and it turns out some alphas are better than others, right? So you can see that in this plot. If you pick alpha equals 10 to the minus 2, then you get this much test score, right? Test RMSE. If you pick alpha equals 10 to the 3, 1,000, you get that much test score. And we picked the best one. Like, we just tried them all, and we picked the best one. So in this particular model, alpha is not controlled by the data. Alpha is given by us. You're mixing up with the James-Stein, which is exactly like that. So it's true, in the James-Stein, it somehow involved all the terms getting combined, so this thing could happen. So you're on the right track. Does anyone else have an idea of what is the issue? Yeah.
I think here we'll do the square of the coefficients.
Okay, the square of the coefficients. Where is that in the formula? Where in the formula is the square of the coefficients?
In the penalty.
Yes, right, in the penalty function. So the penalty function is not just any penalty function. We said specifically the penalty function is you take the square of the coefficient. So you do beta 1 squared plus beta 2 squared plus dot 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 plus beta n squared. You just take all the parameters and you square them up and you add them together. That was the penalty function we used. And this is the specific penalty function that makes it ridge regression. If it's a different penalty function, then it's cheese regression or whatever. Like it's some other regression. Okay? So this is what makes it ridge is this. And again, like I said, cheese was almost as good of a name as ridge because this has nothing to do with ridges. I have no idea why they named it ridge. Maybe it's an acronym. A really, really interesting, dumb G's everything. I don't know. I ran out of ideas. Okay. Right. Ridge. So it's called ridge. I don't know why they call it ridge. A better name is L2. Okay. We have the square of the betas. So what?
I think by doing this, we'll try to push the coefficients value close to 0.
Right. Yes.
So based on that, by using alpha, we try to control these values.
Yeah, this is totally true. So these things, right? Because this is an objective function, we want this number to be as small as possible, and alpha tells you like how much we care, right? If alpha is a big number, we care a lot about the sum of this thing. If alpha is a small number, we care a little bit. Why does it matter that they're different sizes? How does that matter? If the betas are different sizes, why does that matter?
I think there will be more variance if there are different sizes.
What do you mean by more variance? More variance means something is varying more. You're on the right track. Yeah.
I think maybe because it's decreased the effect of lambda. The
Uh-huh.
higher the variance between the betas cause to the imbalance or reduce the effect of lambda.
Okay. So let me make sure I understand. So I think you're saying that they're different sizes. So to me, that's not variance. Variance is when you have something that's random and it can change a lot. So it's true in English, like the word variance could mean both of these things. But let's run away from the word variance because it means something specific. Let's say these are different sizes. So some of the betas are very big, some of the betas are very small. And so what's the conclusion? What does that cause? So if some of the betas are big and some of the betas are small.
I think in general, the difference between the scales of beta
Yeah.
cause to decrease the effect of alpha.
Okay, yeah, I like this. This is a good way to say it. So let's expand this out. I think one way to see what you're saying, and you correct me if I'm wrong, I think you can expand this out. You could do alpha times beta 1 squared, and then you could do plus alpha times beta 2 squared. Okay, and we'll forget about the rest for now. We'll have alpha times beta 1 squared plus alpha times beta 2 squared. And I think what you're saying is, look, if beta 1 is a huge number, beta 1 is like tens of thousands, then you multiply it by alpha, and like the alpha you need for this thing to be a reasonable size is like 0.1, right? You do like 0.1 times 1,000, okay, great. And then over here, if this one is much smaller, if beta 2 is much smaller, then you multiply it by the same alpha, and now you've shrunk it way down, right? So the problem kind of is that you're using the same alpha as a coefficient in front of every single beta, right? Before I said it wasn't a problem. We had beta times x, right? And the betas were different sizes, but the x's were different sizes, and they were all multiplying each other, and they sort of cancel out, right? If the x is really big, the beta is really small, it's all fine. But over here, it's the same alpha multiplying all the betas. And this is really a great way to say what the problem is, which is that in this thing, you're doing beta 1 squared plus beta 2 squared, and like if beta 1 is much bigger than beta 2, then beta 1 squared plus beta 2 squared might as well just be beta 1 squared. Right? If one of them is 1,000 times bigger than the other one, then when you're trying to optimize this thing, it'll just ignore the really small ones and only focus on the big ones, right? It's like if you go to the bank and there's a fine for 1 cent for doing something and there's a fine for $1,000 for doing other things. Like you won't worry about the 1 cent fine. You only worry about the $1,000 fine. Make sure you don't screw that one up, right? And that is exactly what we see in the picture. So in the picture, we have these big coefficients of 75, minus 25, and minus 125, and all the other coefficients are near 0. And then we start cranking up the alpha value. We're like, let's turn up the alpha value and make the coefficients shrink down towards 0. And what does the algorithm do? The algorithm just ignores all the little ones. These ones don't change at all. They're perfectly flat. It's like, okay, just leave those where they are. It's perfect. And it only messes with the big values, right? And that makes sense because the objective function says square them up and add them together. So what is the penalty? It's 100 squared, like 10,000, and then 4 squared, 16. So you have 10,000. You're getting a $10,000 penalty from this red guy and a $16 penalty from this guy over here. And then you're like, okay, now we increase alpha. Please optimize again. And you're like, okay, we'll just ignore that one. Leave that one exactly where it was. We'll take the $16 penalty and we'll care about this one. We'll make this, instead of a $10,000 penalty, we'll make it a $5,000 penalty, right? So basically the algorithm, because of the way we're just adding these things together, even though they're all completely different scales, is effectively ignoring the small ones and only focusing all its attention on the big ones. And it really comes from the fact that we did a sin here. We added things together that were different scales. If you were in physics class, if you've ever taken a physics class, then you go to jail for having things that are different units, right? You'll have like beta will be in meters, beta 1 will be meters, beta 2 will be seconds, and then the physics people will like put you in physics jail because you said meters plus seconds. You can't do that. You can do meters times seconds, those are meter seconds. You can do meters divided by seconds, that's meters per second, that's a velocity. But can you do meters plus seconds? No, then your physics teacher puts you in jail. So that's what we're doing here. We did meters plus seconds. It's not good. So the issue is these betas are different sizes. You cannot just directly add them and it will be meaningful. So we kind of committed a sin here by trying to directly add something that was in front of the division with the thing that is in front of putouts, right? They're not compatible things. And that is why we got a bad result, right? Really what we did, we thought we were doing ridge regression. What we were actually doing was just lower the coefficient of division and leave the other ones the same and see what happens. And if you lower just the coefficient of division, you don't get a big improvement, right? All the other ones are untouched. You basically have done nothing. You've only changed one variable out of like 20 variables. And that's why it sucks. Does anybody else have any ideas or comments to add about this explanation? I think that's the main idea. Any other interesting ways of thinking about it? Yeah?
Are we squaring the coefficients because some of them can be negative, so making squaring it will make...
Yes, that's right, that's right. So remember, we're shrinking towards 0. That's part of the reason we're squaring. The other reason we're squaring, it's the same reason that Pythagoras squares things. So squaring is it makes things an inner product space. You could do it to the power 4. You'll see on Tuesday's class, the videos on Tuesday's class are what happens if you do it absolute value and you get a different behavior. But squaring is sort of the nicest. It sort of corresponds to real life in terms of Pythagoras. So you can think of, if you think of the betas as being perpendicular directions, then beta 1 squared plus beta 2 squared is like the distance squared to the point beta 1, beta 2. So that's why we're squaring it. It's the most natural mathematical operation, and it also takes care of this negative issue. Yeah, great question. Yeah, any other questions or comments? Okay, now we know what the problem is. How do we fix the problem? How do we fix the problem? This is a big problem, right? Let's do this. So basically, what I told you is ridge regression. So far we did it on a mathematical example. It worked great. We do it on a real life example, and it sucks. So how do we fix it? How do we make it work? I'll give you guys a minute to think. Take 2 minutes to think, talk to your neighbors. How are you going to fix it? How are you going to make it work? And then we'll come back with a little brainstorming. I should have had a question for this, but I don't. So just think, and we'll put up your hand and talk. Okay. Let's, anyone have any ideas? How could you fix it? What could you do? There's many right answers. Yeah.
We may standardize or normalize the data.
Okay. Standardize or normalize it. What do you mean by that?
Like we can bring it to all the variables into a range of like 0 to 1.
Okay.
And that will actually erase the difference between each and
Right.
every
Okay.
parameter.
Bring all variables to common range. So, for example, you could make them all between 0 to 1. I believe what this is called standardizing.
Yeah.
Standardizing. Yeah, you should not rely on me for spelling. Okay. Standardize is this one. Bring them all to 0, 1. Okay, how would you do that? So, I mean, it's not between 0 and 1. So you're saying bring it to 0, 1. What does that mean? So here I have numbers that are in the hundreds. Put outs. 632, 880, 200. Oh, I see. Okay, I pretend it's a Gaussian distribution. Is a Gaussian distribution, does that live between 0 and 1? The Gaussian distribution, in my brain, the Gaussian distribution is this one, is a bell curve, and it can be positive and negative, right? Here are the positive numbers, here are the negative numbers. So a Gaussian wouldn't be between 0 and 1. It can be positive or negative. So if you want to do a Gaussian, then we're not doing this 0, 1 thing, which both ideas can work. I think what you're talking about with the Gaussian is normalize. Normalize. That has something to do with Gaussians. So I don't know which one you guys want to talk about first, but they're both valid ideas. Let's do this 0, 1. I think the 0, 1 one is easier to understand first. We'll talk about this one first. So, did you have an idea how to bring it to 0, 1?
I just know like we can do this, but mathematics.
I see. Yeah, you apply scikit-learn dot standardize,
Yeah.
and then it makes it between 0 and 1 by magic. Okay. Yes. True. What is it actually doing, or how would you convert it to between 0 and 1?
Min-max data.
Yes. Okay. Min-max. So what you do is normally the data is between min to max, right? So for example, this column is definitely between the smallest number on here and the biggest number on here. So the smallest number I see is 37. Of course, let's ignore the ... There's going to be other ones. But of the ones we can see, the smallest number is 37. And the biggest number is 1314. So the data is between 37 and 1314. So if I take the interval 37 to 1314 and I subtract 37, then that will be between, so if I do minus 37, then now it's between 0 and, okay, pressure, 1280 something, subtract 40, add 3, it ends in a 7, is it an 8? I'm going to go with 77. Someone correct me. Yeah, okay, we got it. 1277. All right, that's the high stakes math class. You got to subtract 37 from a 4-digit number, right? Like, that's tricky. Okay. So we subtract 37, now it's between 0 and 1277, and if I now divide everything by 1277, then it'll be between 0 and 1. So if you subtract the minimum number and divide by the range, the difference between the max and the min, that'll be between 0 and 1. And so sort of a 0 will represent the smallest possible thing. A 0 means it's the smallest possible, a 1 means it's the biggest possible. And now everything is between 0 and 1. And once everything is between 0 and 1, then all the coefficients, all the x's are on the same scale. And if all the x's are on the same scale, then the coefficients will sort of be on the same scale as well, right? They won't all be equal, of course, because maybe some of them are more important than others, but they should all be compatible, right? They're all multiplying numbers between 0 and 1. So this is a totally valid thing to do, standardizing. I will tell you, okay, standardizing totally works, good idea, makes everything on the same scale. So the main idea is same scale. And this is a valid thing to do. This one has a couple issues. So it works, but I'll tell you a couple issues. Actually, I'll let you guys think. What do you think a possible issue could be? That would kind of throw this off and make it a little unusual. So it is true, everything is between 0 and 1. Like technically speaking, everything is between 0 and 1. But in practice, let's pretend there's some person, and actually this putouts thing is a good example. Look at these guys are hundreds. And then this guy, Wayne Tollison, is a 37. So this guy is a bit of a weirdo, right? He has 37, and yet we took this guy's weirdo answer and we used it on every single person, right? So the min depended on just one person, and that person might be an outlier, might be some person who's not representative of what's going on. Same problem with the max. So if you're doing an operation that relies on the min and the max, and you have a big data set, there's going to be somebody in there who's going to do something weird and throw off your min and max. So the fact that this thing depends on the min and the max makes it quite sensitive to any kind of outlier. So it's sensitive to outliers. And the reason is it depends on the min and max. And you would see that, like, when you would do this, if that happened, you would kind of have the same problem as we had before. So, like, what might happen is this column has a weirdo who's way too small, 37, and maybe there's some other column that has a weirdo that's way too big. Let me see if I can find a column like that I see. I don't know. This column has a 20. I don't know. That's not too bad. But pretend there's a column that has a 1 that's way too big, right? So in the column where there's an outlier that's a minimum, all the numbers will be scaled so they're near 1. So the outlier will be all the way at 0. Everybody else will be like 0.9, 0.95. And then the other column will be the opposite. It'll be like everybody's 0.1, 0.01, and the outlier is 1. And then you're back to the same issue of the scale, right? Where one of them is all numbers near 1, and the other one is all numbers near 0, and you have the same problem. So that's one thing. And another potential bug is, I'll tell you another possible bug, is what happens if you get new data, right? You like run all your data analysis, and then somebody comes with new data, and they give you new people. It's going to change the min and the max potentially, right? So if somebody comes and they're the new min or max, then you kind of have to restart, and it's like complicated to keep track of what's going on. So if the min and the max change as you get more data, things will change, and that can be quite bad. So changes with data set. Okay, so it's a nice simple way to do it, but it will cause some issues. That changing thing is especially problematic if you have a test set and train set. That can happen. So sometimes people standardize on the train set, and they standardize on the test set, but a 0 on the test set standardized and a 0 on the train set standardized are two different things, right? One of them represents the minimum value from the test set, one of them represents the minimum value from the train set, and so it's easy to confuse yourself and have all sorts of bugs that take you all day to figure out. So standardizing possible, works well in simple situations, but because of these issues, it can get worse. So a little more complicated, but more useful is normalizing, where we make it a Gaussian. And so what you can think of is if you plotted the distribution of, say, the putouts, what would it look like? Ideally, it would look like something like this. So here is the putouts on the x-axis, and we're going to do a histogram. There'd be a lot of people who have sort of a middle amount of putouts. And then a few people are outliers. Like this guy who had 37 is all the way over here. Here's x equals 37, and there's one guy who's this weirdo. Sorry, Wayne, for calling you a weirdo. So there's this one guy who's an outlier who's got 37. There's another guy who's an outlier, Willie, who's got 13, 14. He's all the way on the other side, right? So 13, 14 is like all the way over here, 13, 14. But most of the people will sort of be in between, in the middle somewhere. And hopefully the data would be sort of this Gaussian distribution. Okay, that was terrible. Let's try one more time. Gaussian distribution, smooth up and down. Okay, that's not too bad. And if it's a Gaussian distribution, it has two parameters. It has a mean and a variance. So there's the mean mu, and it has a variance, or a standard deviation, which is sigma, which is like how far it typically is. And the nice thing about the mean and the standard deviation, you can measure the mean and the standard deviation just by the formulas that we've talked about many times in class. And they are somewhat sensitive to, like they still depend on these guys, the 13, 14, and the 37, but those people only have a 1 over n contribution, right? So this guy, 37, instead of being completely determining the min, he is pulling on the mean with size 1 over n, where n is the number of people. So this person being 1/1000th of the data set, even if it's a very small number, won't change the mean very much. And so it's okay to have outliers. And the other nice thing, if you do this Gaussian thing, is that if new data comes in, presumably the mean and the standard deviation won't change, right? So if the mean and the standard deviation of the baseball players in this data set was 500 with a standard deviation of 10, then if there's another one, it should still roughly be 510. And if it's a little bit off, we can still use the same scale as before, and we'll just get numbers that are not exactly mean 0, and that'll be okay. So to do a Gaussian, instead of subtracting the mean and dividing by the max, what you do is you do x minus the mean divided by the standard deviation. And if you do x minus the mean divided by the standard deviation, then now the numbers will be mean 0, and they will typically be between -1 and 1, but like some of them will be between -2 and 2, right? 95% of them will be between -2 and 2, and so on and so on. So this will be like a Gaussian. This would be like a mean 0, variance 1 Gaussian. Mean 0 and variance 1. Okay, and then for those of you that like physics, this will also handle things in terms of units. So if you think of x is in some dimension, so if x is in meters, if x is meters, then sigma, the standard deviation, will also be in meters. And so you'll have meters divided by meters, and so it will become a dimensionless quantity. It'll represent like how many multiples of this typical length are you, right? So if the typical scale is 2 meters, it'll be like how many multiples of 2 meters are you? So if you're a 3, that means you're 3 times the typical length. And the nice thing is, then we can really compare things. If they're dimensionless, then it does make sense to add them together and square them, right? So you say like, how many meters are you in units of 2 meters? You're 3 units of 2 meters, and then you're 4 units of 5 seconds. Like that makes sense. You can add up those 2-dimensional numbers, 3 and 4. That makes sense. You can't add up 3 meters and 4 seconds, but you can say how many multiples of a yardstick you have. So that is called normalizing, and this one I think is a little bit better. You do have to write down, just like you have to write down the min and the max, you have to write down these numbers, the mean and the standard deviation. So I'll show you how to do that in a second in the code, but are there any questions about this idea? You might have seen this idea before. Sometimes this goes by a z-score as well. Sometimes this is called a z-score. Z-score. So a z-score of 2 means you're 2 standard deviations above the mean. There's 2 you are equal. If z equals 2, then x equals mean plus 2 sigma. You're 2 standard deviations above the mean. So that's another way to think about it. We're converting all the things, instead of being in raw units, are in terms of the z-scores. Okay. Questions or comments about this? If you've never seen it before, I probably went way too fast. So hopefully you've seen it a bit. Feel free to ask. Okay, people are nodding, people are okay. So let's see how it works in the code. It's actually quite simple. And again, you can use like scikit-learn.normalize, but I don't know what that does. So and then you have to spend a lot of time reading what it does. And it's actually, if you look at the math, it's not that complicated. And I had this conundrum the other day when I was making this. I was like looking up how scikit-learn.normalize works, and I gave up. It was like too much reading. I was like, nah, this is stupid. I'm just gonna do it by hand. So at the bottom of the data set here is how to normalize. And I made a little function, my normalized function. This is like a better version of the scikit-learn one. Why is it better? Because I didn't have to read the documentation. I just made my own. Okay, so you can like use the official one, but here is what I did. So it returns a standardized version. I should say normalized, because standardized means something else. Let's replace it. Normalized version of the data frame. So you input the data frame df, as well as the list of means and standard deviations. And the list of means and standard deviations is useful if you ever want to convert back, right? So if you know that z equals 2 and you want to convert back to x's, you need to know the mean and the standard deviation. And so I return those lists just in case. So I take the mean, I take the standard deviation, so that'll be 2 lists of numbers for every column. What is the mean and standard deviation of every column? And then I do the function that I said, subtract the mean, divide by the standard deviation. I'm gonna make that a little bigger so you can see. And then I just return the 3 things. So the normalized, data frame, the mean, and the standard deviation. And this is what it looks like. So uncommon to run this if you do this. So x was our data frame. Do I have to run everything? He's gonna yell at me? Okay, run all. I took too long explaining things. Run all. Okay, so x was the everything except the salary, and I ran the function, I normalized it, and I said my normalized function of x, and you get back 3 things. You get back the means, the means, So here are the means of different columns. So let's look at putouts. What was the mean of putouts? Putouts, the mean was 290, whereas the mean of division was 0.5. So division was either 0 or 1. About half the people are 1, half the people are 0. Putouts is a number that is much bigger, is like a mean of 290. And here are the standard deviations. So for putouts, the standard deviation was also like 250, which shows you that there's big range. Right? Some people are near 0, some people are like 500. The other ones like division, again, it's really small, standard deviation like 0.5. So this makes a new data frame called x normalized, which is like x, but everything is numbers that are on the scale like negative 2-ish to 2-ish. Like 95% of the data should be between negative 2 and 2. Actually, yeah, why don't we look at it? Let's do an x normalized. What does it look like? Show me. And here we go. So here are the numbers, and everything is normalized now. So this person, it's not that they got negative 0.5 home runs, it's that they got half a standard deviation below average for home runs. This is a below average home run hitter. This guy is 1.7 standard deviations above average. Is there anybody who's really good at home runs? No, this guy's the worst. Wayne, you really let me down today, Wayne. Minus 1 standard deviation. So this guy's a bad home run hitter. Any cool numbers? Whoa, this person has a 3.6. That's a huge, what column is this? Putouts. This guy is amazing at putouts. Look at that. Killer. Okay, I don't know what a putout is. Okay, so we converted it all to numbers that are on the same scale. And now, if we rerun everything should work better. You do have to be careful about your handling here. So I have two data frames now. One is called x, and one is called x normalized. And if I was writing everything from scratch, I would write it all with x normalized, but I already wrote all the code using x. So I'm going to do something slightly bad, is I'm going to say x equals x norm. Actually, why don't we do this? Let's do x raw equals x. So we'll save the data frame that x is into x raw. And then we'll do x equals x normalized. Normalized. And now everywhere that was an x before has been replaced by the normalized thing. And now I can just rerun the code from before. And we'll see how it changes. So let's go rerun the code from before and see how it changes. So don't rerun this one that loads it, because then we'll have done nothing. Okay, and hitters hasn't changed. Okay, but this works. So the train test split, do it on x, which is now normalized. And now let's get all the coefficients. So the coefficients before, remember, were on different scales. Minus 116, 0.03. Let's run it now and see what happens. All right, so now they're all kind of the same. They're all in the tens to hundreds, which makes sense because you have to multiply by a number which is negative 1 to 1 to get something that is like hundreds. And some of them are still much bigger than other ones. And that is just showing you that some of them don't matter. So like RBIs really doesn't matter very much. C at-bat seems to matter a lot, but at least none of them are like thousands different. You know, they're like on the same scale in some formal sense. So that's good. And you can really see it if you do this ridge regression plot. So let's do this ridge regression plot. Run the ridge regression for every single value of alpha, and here's what it looks like now. So it looks a lot better than before. Before, basically there were like 3 coefficients that mattered and nothing else changed, and now you see so many more, like everything is changing, and everything is playing a role. So it's not like 1 or 2 are changing, they're all sort of changing. So this green one starts out the most negative, but they all sort of shrink in towards 0 as you increase the ridge regression. So this looks a lot more promising. Everybody is playing. And now let's look at the validation. So again, we're going to just look at the test set and do this plot like before. And here's what it looks like now. So before, it only went down by 1. Look, the scale here is completely different. This is 340 at the top. This is 315. So this is like a 20% improvement, something like that. Maybe only 10% improvement. So quite a bit better than before, and it really does go down a lot. And that is the optimal value we found using our test set. Okay, so in practice, what you would do is it would be just like project 1, where you would do this train test split, you would find the optimal value, which we found 123, and then you would rerun the whole thing on the full training set using alpha equals 123, making sure to normalize everything like before, right? And then that way, everything is consistent and you should get the best possible model. So that would be just like you did on project 1, except project 1, most people did variable selection, which is another way to reduce overfitting. Here we're doing ridge regularization. Okay, and so it's important you don't skip this step of making everything the same scale, or it really just won't work. If things are different scales, it'll just do something silly like only look at one variable. Okay, any questions or comments about this idea? Okay. Okay, a couple other quick things. Okay, so here's some code where you can try different parameters. It's sort of this one, we tried all of them at once. So I'm gonna skip that. But here is another function that is quite useful. It's called RidgeCV. RidgeCV. So in practice, I only did one training set and test set, and I just did everything by hand, so you can look through the code and see how I did it. It looks a lot like your projects. There is a function called RidgeCV. And if you do RidgeCV, you just tell it the grid of alphas you want to try. So you give it the list of alphas, and it will automatically do cross-validation. So it will split the training and test set into 10 folds, and it'll do ridge regression 10 times using a different test set every time, and it will automatically try to find the best value. And okay, if you look at the picture now, here's what the picture, or what does it say now? Now it says the best value was the largest value, and the MSE was not very good, and that's because it's still using the thing where they were different scales. So I'm going to rerun it now. Xtrain has now been updated to the normalized one. So let's rerun it and see what happens. And the best value it found was 77. So a little bit different than what we found before of 123. And here is what it looks like. And it found the RMSE of 316, which is pretty close to the minimum we found. So we found right around 316. And RidgeCV kind of does it automatically. You don't get a nice picture though. So I don't know what it does under the hood. It does some crazy stuff, and it finds this value, and then it's kind of like magic. So it's a little bit of a black box. If you want to understand what's going on, it's sort of better to do it by hand. I'm sure this is more efficient. And it's nice that it's cross-validation instead of just one test set. So that's a good function to know. Okay. So the rest of the stuff I have is some theory stuff and some fun stuff. But this is like the main message that you got to take home. Is if you're going to do this ridge regularization, if you're going to mess with the parameters themselves, if you're going to treat the parameters beta like they matter, then you got to make sure they are the same scale, or otherwise nothing makes sense. Any questions or comments? Okay. All right, yeah, so we have some hardcore math here that we might do, but we also have one fun little thing. So I'm going to do the fun thing first, because fun is fun. So this is a blog post I read that I really liked, and it's called "Too Much Efficiency Makes Everything Blank." I want you to guess what is the blog post. It's in this little tab over here. So this is the title of the blog post. And yeah, you'll be able to read it. I'll post it online, and then I'll talk about it briefly. But it'll be fun to see what you guys think. I'll give you 1 minute. Put in your favorite word. It doesn't have to be accurate. Okay, I'm very curious what you guys said. Really is kind of just for fun here. Too much efficiency makes everything what? It makes it predictable. That would be nice. Things being predictable would be good, right? Too much efficiency makes things complicated. Well, it makes it doubtful, time-consuming, inaccurate, complex. I guess that's the opposite of predictable, maybe. Worse. 5 people said worse. Work better. Yeah, see that efficiency, it means like working better, right? So like how could you have too much efficiency? Like too much work better? It seems silly. Makes it uninteresting. Yeah, that's possible. This common answer, worse, is actually the name of the blog. Too much efficiency. Maybe you guys peeked at the thing. Will it load?
It's the first name.
Oh no. You guys caught me. Okay. So too much efficiency makes everything worse. It makes it worse. And if too much efficiency makes everything worse, how is that possible? I think this is a really counterintuitive idea, and it's related to overfitting. And so this guy, I know this guy because he's a researcher who studies like my corner of machine learning research, on infinite neural networks and that kind of thing. And so he has this really nice blog post talking about Goodharts' law. So Goodharts' law, I have a little thing over here. Goodharts' law says, when a measure becomes a target, it ceases to be a good measure. So, and the example they have is with nails. So imagine you have a bunch of nail factories, and you're the owner of the nail factories, and you're like, I'm going to reward the nail factories for being good, right? When they're good nail factories, I will give them more money, and then they will be better nail factories, right? They'll make me more nails, and I'll be everyone will be happy. They'll be happy. I'll be happy. And so how will I reward the good nail factories? Maybe I will measure the number of nails that each nail factory makes, right? And here's the problem. If you measure the number of nails that each nail factory makes, you're going to show up to the nail factory, and they're going to have thousands and thousands of tiny nails. And you're going to be like, well, yes, you have a lot of nails. You did great on the score, but now you have crappy nail factory. So I wanted a good nail factory that made lots of nails, and then now I have thousands of tiny nails. This is useless. All right, so don't do that. Don't tell them the number of nails made. Tell them the weight of the nails made. See, because then they can't cheat by making lots of small nails. But then they'll cheat a different way, is they'll make a few giant heavy nails, right? And so Goodharts' law is saying whatever you choose as the target will be a bad target. Because as soon as you pick what it is, people will cheat to make that the thing. And this is exactly the idea of overfitting, right? So in this blog post, he has this really nice demonstration. You can tell this person is a machine learning researcher and not an artist by this comic. There's two people talking, and this person says, this is the thing we care about deeply. We must optimize it. Look at this beautiful thing, right? I want a good nail factory. And this person says, well, that thing is immeasurable. What does it mean to be a good nail factory? That's silly. Let's look at this easy to measure thing. Here's the easy to measure thing. How much do your nails weigh? We put them on the scale, we measure them. What if we just optimize that instead? Okay, and why is this related to what we're doing in this course? In this course, everything we do is like this. We have the true RMSE, right? This is what we actually care about. The true error, which is, in real life, how does it do in real life? The expected value of our estimate minus the real thing squared. This is what we want, right? But we can never actually estimate the true RMSE. The true RMSE would mean going out and getting new data sets. We can never look at this. I shouldn't have done this in black. I should have done this in the cool color. Do I have a rainbow? There's a rainbow here somewhere. Okay, well, I don't know. I'm going to do purple for rainbow. This is the rainbow. This is the cool multicolor thing, right? The true RMSE, the multicolor guy. And the boring thing that we do instead, we cannot measure the true RMSE, is we do either the training RMSE or the test RMSE. But either way, we just have some finite sample, which is the sum of y hat minus y squared, averaged over our data set. Right? And we can't do this one. We just hope that this one is close to that one. That's exactly what's going on in our data science course. And what happens is, and you've seen many graphs like this, is first, you have the well-aligned phase. So as you go and you're optimizing, the good thing, the rainbow color thing we want to optimize, that is also improving. But the proxy objective, the easy to measure thing, that is improving too. And yay, the thing I care about is improving. So the cool thing is improving. We have peace, love, puppies in the objective we care about. Everything is going well. That's the well-aligned phase. And this means things are going well. You don't have overfitting. Things are working the way you want. But then you have this overfitting situation, which is the proxy is getting better. You're fitting the training data better and better, but the thing you care about, the actual test error, is not improving, right? So, hey, the thing I care about stopped improving, right? The thing that you're measuring keeps improving, but the thing you care about stops improving. The nail factory isn't getting any better, but they are sure making some heavy nails, right? That's what's happening. And then this whole blog post is about the next phase, which is the strong version of Goodharts' law, which is that actually, if you keep going, it gets even worse, right? It goes up, up, up. And this is what you saw with overfitting in the first project, this U-shaped curve, right? And it's very classical in machine learning, but the point of this blog is that it applies to lots of things in real life. So Goodharts' law normally says, okay, as soon as you make an objective, it's a bad measure, but actually the strong version says, when a measure becomes a target, if it is effectively optimized, then it will actually get worse. It'll be worse than if you hadn't said anything at all. And he has lots of nice examples. So here are some of the examples he has. Goal, educate children well, right? The thing we want to do is educate children well. How do we educate children well? Well, we like measure how well they do on standardized tests. But then people start to only teach the test, and then you're actually doing worse at educating children well. Rapid progress in science. Okay, how do you do it? You pay people for every time they make a publication. I was like, oh, that's not good. So this happens all the time. And why am I bringing this up now? It's a great blog post, you should read it. That's one reason. But the other reason is, how do you stop this from happening? How do you stop it from happening? And there's a bunch of different reasons, but here is the one I want to talk about, which is you add regularization penalties to the system. So just like we added in ridge regression, we added this penalty term that says, don't make the betas too big, keep the betas small. You can do that in real life. You can do that for anything. And I like this example. Add a billing mechanism to SMTP. SMTP is how internet emails work. When you send an email, it goes over SMTP. Right now, you can email anybody anything, as I'm sure your spam box is aware of, right? You get millions of emails that have nothing to do with you because it's free. But what if it costs like 1 cent to send an email? This would be like a regularization term, right? The cost of doing an email, before it was like whatever you had to do, and now we're saying plus 1 cent every time you send an email. And for people like you and me who just send a couple emails every day, it's no problem. I can afford like 3 cents a day of emails. But for people who send 1 million emails a day, those people will get penalized and they'll have to change their behavior. It is exactly like what we were doing here, right? So we had the ordinary thing plus this regularization term. And this regularization term keeps things from going too crazy. It stops any kind of weird, bad outcome. Any kind of overfitting, it will reduce that by keeping it from happening. Okay, so yeah, other examples. Tax the number of bits of information stored about users. So companies kind of store so much information about you that they don't actually need. And the one way you can do it, you can say, like, every time you store a kilobyte of information, you have to pay 1 cent, right? So then they're really going to be like, well, in that case, I only need to store the things I actually need. Okay, so fun blog. I'll post it on the website for you guys to check out. And I just thought it was a really cool way to connect what we're doing to real life, right? Because we've seen this before for data sets, and the point is it applies to everything. And this regularization idea of keeping things from overfitting by adding a penalty term is something you could think of in real life. And also, I think this is also leading into other forms of regularization. So far we've seen ridge regression, L2 regularization, which is this penalty term. Next class, we're going to do lasso regularization, which is L1 regularization, which is adding the absolute value of beta 1 to the power 1. So instead of to the power 2, it's to the power 1, and that ends up having a big difference somehow. But there are there's infinitely many different regularization ways, and it's all about controlling how things go in this. And there's some of those ideas are here. A really simple one is early stopping, and this is used in machine learning a lot. So it's like, just turn off the machine before you get here. So what we do is we just stop. If we stop here, then we're good, right? Or maybe stop here, right? So stop before this thing gets too good. Then we'll just stop, and that will prevent some overfitting. So that's called early stopping, and I'm sure that's somewhere in here, early stopping. Yeah, there we go. Here's another idea. In machine learning, it's common to monitor the validation loss, and then you stop when it starts to go up. And there's some ideas in real life. So this is a nice blog to get some real life insight on different strategies other than adding penalty terms. So there's early stopping, there's other interesting things. Adding noise, things like that. This is, in machine learning, there's a thing called dropout, where you randomly turn off some neurons in the network. This dropout thing, or injecting noise into the system, there's a really famous video when they were making these robots. There's this company called Boston Dynamic that makes these walking robots. And the walking robots are trying to walk, and they're pretty good. And then some jerk from the factory comes over and kicks the robot. I don't know if you see in these videos. So the poor robot's trying to walk from one side of the room to the other side of the room, and the employees of the company keep kicking it, right? And the point is, if the robot is able to navigate with people kicking it, it can handle any kind of weird uncertainty. It's not going to memorize the room and only do the same thing over and over again, and as soon as it gets to a new room, it's going to fall over. If people are kicking it, and if you're able to optimize under noise, then you're going to be sort of robust to changes. Anyway, so lots of good ideas about regularization here. We'll do more regularization on Tuesday's class. Any questions or comments about any of that stuff? Okay, in the last 10 minutes, I'm going to tell you about something which is related to all this stuff. which is exercise 3. What does multicollinearity mean, and why is it a problem? So this is, I think, I've seen a few people talk about this, so I want to talk about it a little as well. And it's related to what we're doing, because this ridge regression stuff actually solves partially the issue of multicollinearity. And I'll show you a nice little picture. I'll give you the 10-minute version with just a nice picture of what is multicollinearity and why ridge regression solves it. So first I'll let you think for a minute, or let's say 2 minutes, on what is multicollinearity, what does it mean to you, and why is it a problem? Okay, 30 seconds left. Just put in any old 30 character idea. I'm not going to give more time just because we're getting close to the end here. But whatever you put in will spark some interest. Okay, let's see. What do people say? Multicollinearity means multiple correlated variables. Yeah, so it really is the idea of correlation between different variables in your regression. So maybe in this hitters data set, right, what were the columns like? There was at-bats and there was hits. And of course, if you go to at-bat, if you're batting more often, you're going to get more hits. So those things will be correlated. And multicollinearity is the idea of this correlation being really high. So great concept there. So correlated, one variable related to another, and it's the problem of them being highly correlated. Why is it called multicollinearity? I don't know. It should have just been called high correlation or something. So yeah, lots of people got this idea. I think people know what this means. Sometimes people say this is a problem, and for some things it is a problem, and for some things it's not a problem. So why is it a problem? I don't know. Good. It turns out it's not related to overfitting. So you can fit perfectly well if they are or not. It is related. The bottom one got it right on, which is the unstable coefficients. And let me give you the little 2-second cartoon version of why this is. So let's pretend there's two variables. Let's pretend there's x and y. Okay, let's call them x1 and x2. And we're trying to fit y equals beta 1 x1 plus beta 2 x2. Okay, that's what we've been trying to do this whole time in linear regression. And I'm going to do something really silly. What if actually x1 equals x2? This is perfect correlation, perfect 100% correlation. And here is the problem, is that beta 1 x1 plus beta 2 x2, this formula I wrote over here, you can now factor it as beta 1 plus beta 2 x. So even though there's two variables, beta 1 and beta 2, in this perfect 100% correlation situation, the only thing that matters is the sum of the two variables. So two variables, beta 1 and beta 2, but only beta 1 plus beta 2 matters. So this is kind of an overdetermined system. There's multiple ways you can have the same solution. If beta 1 equals 2 and beta 2 equals 3, that's the same thing as beta 1 equals 1 and beta 2 equals 4. So they sum to 5, it's going to be the same model no matter what. And so what this means is when you run this thing, you will get very different answers. Sometimes you'll get beta 1 equals 4, beta 2 equals 1. Sometimes you'll get beta 1 equals 5, beta 2 equals 0. There's lots of different ways you can come out. And that's because there's lots of different solutions that have the same beta 1 plus beta 2. So the individual numbers, beta 1 and beta 2, will be all over the place. However, the estimate for y will still be fine, because beta 1 plus beta 2 is the thing that actually matters, and that can be okay. So what this leads to is beta 1 hat and beta 2 hat will be unstable. And by unstable, I mean you can like rerun it with very slightly changing the data, and it'll change completely. And I'll say, but beta 1 hat plus beta 2 hat is okay. And beta 1 hat plus beta 2 hat, that is the thing that is predicting y. So the predictions for y will still be fine. Predictions for y are okay. So when is this a problem? It's if you really want to know the individual coefficients, it's a big problem. If the only thing you want to do is estimate y, like get as good of an estimate as you can, then it's fine. And that is what's happening. That's the 2-minute version. Now let me show you what this has to do with ridge regression. The way this comes up in the math. How does this come up in the math? Like, why is this unstable? Unstable has a nice mathematical definition. I can tell you exactly why. So the optimal beta, when you do beta hat, think of it as a vector. It's beta hat 1, beta hat 2. So there's going to be a little bit of linear algebra. The optimal beta, when you do it, turns out can be written in terms of some simple matrices. And I'm going to write it like this. It's going to be x transpose x inverse times x transpose y, where x is the matrix. X is x1, x2, and here are the row 1, row 2, all the way up to row n data. So x is the matrix, which has a row for every single data point, and it has a column for every feature. Just like when you do a pandas data frame, it's this matrix. So it's a n data by 2 matrix. And if you multiply that matrix by itself, if you do x transpose times x, you get a 2 by 2 matrix. So this is 2 by n data, and this is n data by 2. So if you multiply them together, you get a 2 by 2 matrix, and if you take the inverse of that 2 by 2 matrix and you multiply it by this vector, y is the vector of the y values. That'll be a vector of size 2 with the 2 beta hats. So you can write it in this nice way with this inverse. And this unstable idea has to do with whether or not this matrix is invertible. So this beta hat 1, beta hat 2, it turns out is really this unstable, you can say is it invertible? Unstable equals bad inverse. And there's lots of ways you could say it has a bad inverse. You could look at the eigenvalues, you could look at the condition number. There's a lot of different ways to say it. But basically this matrix is very close to not invertible. Right? Just like the number 0.001 is very close to not invertible. It's too close to 0. Some matrices are very close to not invertible. If you look at their determinant, the determinant is close to 0. Things like that. And when it's not invertible, in that eigenvalue direction, you have this unstable thing. Okay. What is the point of all this? The reason I want to show you this is when you do ridge regression, you have the same exact formula, but there is one extra term you add on. And the term is so small, I can sneak it in here. So when you do ridge regression, you have a parameter alpha. Let's do it in purple. So instead of having just beta hat, you have beta hat, and it depends on alpha, right? Because you tell me alpha, I redo the whole thing, and I get a different answer. And this beta hat has an alpha, and you redo the whole thing. So there's a beta hat 1, it depends on alpha. Beta hat 2 depends on alpha. That's exactly what we were looking at in these graphs, right? We were looking in these graphs, as you change alpha, how do the coefficients change? For every value of alpha, you have beta hat 1, beta hat 2 of alpha. What is the formula now? And there's one very simple thing you do. is you take this matrix, X transpose X, and you add on, you do plus alpha times the identity matrix. And okay, maybe I can make it a little bit bigger so we can see it. You just do plus alpha times the identity matrix. So of course when alpha equals 0, it's just not there. But when alpha is a big number, you're adding the identity matrix onto this X transpose X matrix. So it goes from being a 2 by 2 matrix that has a determinant near 0, maybe. You're adding on alpha to it. That makes it easier to invert. It makes all the eigenvalues go up by alpha. It makes it easier to invert. It makes the condition number better. And that makes everything more round. And I'll show you a picture of what this looks like. So that's algebraically, when you add on alpha, when you do ridge regression, the inverse gets easier to do, and you get more stability. So it kind of reduces this problem of multicollinearity is when you have a repeated column here, and so it's not invertible, and you're making that okay. So even if it's perfectly, even in this 100% case, by adding this term on, it makes it invertible, and everything will be fine. And I'll show you a picture of what this looks like in Desmos. So here is what it looks like in Desmos. Let me just do just this one. So here is, I took some data, and in this plane, I have plotted on the x-axis, I have beta 1. On the y-axis, I have beta 2. And then this blue curve over here, which is a big cone, that is the loss you get as a function of beta 1 and beta 2. So beta hat 1 and beta hat 2 are the minimum of that guy. Right? Beta hat 1 and beta hat 2 are saying minimize the mean squared loss. And you can see that it has this kind of funny direction over here. And that direction gets worse and worse the more correlated the matrix is. So this is a correlation of 0. If I go to a correlation of 1, you'll see what happens. So as the data becomes more and more correlated, you have this, it goes from having a nice bowl shape to being a really stretched out guy. And this is multicollinearity. Can I zoom out of it? Let's zoom out of it. And you can see, when you have multicollinearity, there are a lot of different beta values that give you almost the same answer. You're very stretched out. There are many different beta values that are sort of near the bottom of this valley. So you don't know where the bottom is, because it's sort of like all these points. It's like in the Grand Canyon. Where's the bottom of the Grand Canyon? Well, it's going to need a lot of work to find the bottom of the Grand Canyon because it's so long. That is multicollinearity. And let me show you what happens when you add on this alpha value. So this alpha value, right now it's 0. What happens when I add on to the alpha value? It kind of smooshes it to make it more round again. So it's adding on just the cone at 0. It's adding on alpha times x squared plus y squared. That's what the regularization does. And if you add it on a little bit, it makes it rounder. So it kind of makes this problem of multicollinearity, where in the thing you are, it makes it better because you're making it rounder. It also moves things towards 0, right, which is not good. You don't want to move too far towards 0, but it fixes this multicollinearity problem. Okay, and you can see it mathematically from this formula. I'll post a note online on where this formula comes from and what it means. But this is the short version, the short picture version of why ridge regression helps mathematically, not just for reducing the test error and reducing overfitting, but mathematically it makes things better as well. Okay, I'll stop there. I'm a little over time. Thank you for your patience. We'll see you guys on Tuesday.